Thank you for joining us at the Charge Virtual Conference on EV Engineering. The topic of this session is pressure, equalization, and battery packs and edge case analysis. There'll be a Q&A after the presentation, so submit your questions at any time by clicking the Q&A button. And please welcome our speaker, Matt Good from Donaldson Company. Welcome, Matt.
Thank you for that introduction. As mentioned, my name is Matt Good, and I'm a product development engineer at Donaldson Company in the Integrated Venting Solutions Group. And today we're going to be walking through pressure equalization in battery packs, an edge case analysis. Today, I'm going to walk through a quick overview of what Donaldson is, and then we're going to be discussing why we have to vent in automotive applications. Next, we'll define what an edge case is, then walk through edge cases in battery pack enclosures, followed up by designing around these edge cases. Lastly, we'll have a conclusion slide followed by question and answer. So what is Donaldson? At a glance, this is a 100-year-old company that is focused on providing filtration solutions that improve people's lives, enhance customers' equipment performance, and protect the environment. Working towards this goal is 1,000 scientists and engineers globally, with 46 manufacturing plants around the world, creating some very innovative venting and filtering solutions in a variety of different marketplaces, including engine air filtration, engine fuel liquids, industrial dust fumes, compressed air process filtration, and what we'll be discussing today, venting. Now, at the core is three main pillars, one being our corporate technologies group, which is developing brand new EPTFE coatings, absorbent systems, and alternate medias to what we have today. And this is the research that's 5, 10, 15 years into the future. Coupled with this is our engineering solutions group that works between the customers and the research and design to develop strong collaboration and innovative solutions for the customer demands. So we take voice of customer, work with those scientists, and develop solutions that meet and exceed those requirements. So what we offer is working together with you to optimize your design, process, and performance, while doing some pretty heavy research, development, and validation to ensure that we're going to meet and exceed those requirements. Now, with this, we're able to develop our own material range that's tailored to your application and providing a global expertise and the latest equipments and assembly methods. With all this, we're able to take care of your component needs from beginning to end. Now that we know a little bit about Donaldson, let's dive into automotive venting battery packs and why we even need to vent. So if we take a look at a battery pack, as seen below, we have an enclosure with some battery components on the inside, some free air, and a vent installed. Now, as this component either has a temperature change or an elevation change, there will be a change in relative pressure between the outside of the battery pack and the inside. And a vent will enable this delta pressure to be eliminated. Now, if this delta pressure is not taken care of, it could lead to seal failure or deformation of the enclosure. Now, if we take a look at what's actually happened during these venting scenarios, we either have a pressure falling or a pressure rising event. When we have pressure falling, we have air flowing into the battery pack, and when we have pressure rising, we have air being released from the battery pack. Now, while this is occurring, we want to make sure that we keep dust, water, and other contaminants out of the battery pack. This will ensure the integrity of the components that are on the inside and ensure our seals and gaskets do not get damaged during the life of the vehicle. Now, as we take a look at a seal specifically, we typically have an enclosure, an O-ring, or other gasket material, and a cover. And in normal pressure as assembled state, we'll have good compression and good seal along that sealing surface. But under extreme vacuum and extreme overpressurization events, the cover could deform, causing a leak path through the gasket itself, which in the field could result in water, dust, or other contamination getting into the battery pack, causing premature failure for the customer. Now, a nice, robust venting solution that's been designed around the edge cases and nominal performance will prevent this from occurring. And if we take a look at the current industry and what is available on the market today, we can kind of break it up into two major categories. The first being single stage venting. And this is primarily a breather vent, which allows air to either go in and out, a burst vent, which only opens up at a certain pressure and once opened will remain open, or a resealable vent, which will enable airflow in only one direction, but will only open up after a certain value. Now, we've seen a lot of companies in this market space also starting to introduce dual stage vents, which take multiple single stage applications and then couple them into a single component. And we can couple these into two major categories, a burst and breather vent or a resealable and breather vent. In both of these cases, we have a breather vent, which enables airflow in and out of the battery pack, and then a secondary function, either a bursting or a resealable, which enables a secondary, either high airflow during emergency degassing or during normal operation. Here at Donaldson, we've developed two solutions that couple into this dual stage strategy, which is dual stage burst and our dual stage flex. Our dual stage burst uses a media that when it hits some burst pins will open up, versus our dual stage flex encompasses our media with an elastomeric flexible valve, which will open up, enabling high airflow. Now, at the core of the Donaldson technology is our Tetra-Tech ePTFE membrane material. And if we take a look at what expanded polytetrafluoroethylene is, it's basically an expanded Teflon material. But at zoomed in at very high scales, as seen on the right, it's a very interlinking material, which enables only air and certain materials to pass through, yet keeping oil, dust, and contamination out. Outside of the venting solution application, Donaldson uses this material in other facets within multiple industries, enabling for high confidence in manufacturing and low cost to customer. Now, as we take a look at dual stage vents, there are four major functions that these have to perform. One is sealing and guarding the battery pack against water, dirt, and debris. Two, we need to provide continuous pressure equalization. So this vent needs to continue to either breathe, burst, or reseal to make sure that we're keeping the pressure constant inside this battery pack and not causing seal damage. Three, we need to allow effective ventilation. So if we have an extreme venting scenario, we're able to compensate for that extra pressure or extra vacuum. And four, we need to help ensure proper mitigation in an emergency degassing or thermal runaway event. Now that we know a little bit about Donaldson and about venting in automotive applications, let's dive into edge cases. The definition of an edge case is events that occur at extreme operating parameters. And for our discussion, this will be edge cases with low occurrence over the life of a vehicle. Taking a look at electric vehicles, we're breaking this up into normal driving. So that's tier 1, tier 2 charging at your house every day, maybe a casual drive up the Rocky Mountains, some crosstown commuting to get groceries or pick up the kids, and a few puddle splashes on a rainy day. Now, our edge cases are going to be things such as DC fast charging, where while it doesn't occur every day, this is an event that can occur and will create some interesting loads within the battery pack. Hill climbs, a competitive sport where people race up a hill in an extremely fast amount of time. Water fording, driving through a creek or small river because we're on an off-road trail going where no one's gone before. Air transportation, transporting our components via aircraft or even a complete car via aircraft around the globe. And rock impact. While we're four-wheeling, we accidentally slide on top of a large rock, which impacts our battery pack enclosure. Now, some quick housekeeping. The values presented in the following edge cases are specific to the setup used by Donaldson, and every single battery pack will have different pressures, temperatures, and edge case scenarios specific to that system and end application. So please keep that in mind when we take a look at either values mentioned or temperatures on the next few pages. Additionally, the pressure and temperature values were derived for the following edge cases using these assumptions. 1 is 20 liters of free air volume. 2 is a temperature range from -40°C to +80°C. 3, assuming a rate of climb of an aircraft of 2,500 feet per minute. A Pikes Peak race time of 30 minutes. And we remove time scale from each event. So we're only going to be discussing what the max temperature and pressure is, but not how fast we will reach those values. So the first edge case we're going to be talking about today is performance. And with these edge cases, I'm going to try to paint a small story. So let's imagine we're in Alaska, we're on an off-road trail, and we're really pushing our car to the max. We're really flying around the corners, putting the pedal to the metal. With this extra demand on the battery pack, we could see an increase in cell temperature within the battery pack. Now, as this temperature rises, we could see an increase in the pack pressure. Compared to normal operation, this pack pressure and pack temperature would be slightly higher and slightly above that normal operating temperature condition. So something we'd want to keep in mind when we're designing venting. Next is rock impact. So we're up in Alaska, we're driving around, and then we notice a nice rocky trail in front of us. So we slow down and we start crawling over the rocks, but we accidentally have the undercarriage hit a rock. During the impact with the rock, the battery pack enclosure could deform. And during the deformation of the cover, there would be an instantaneous change in free air volume within the pack. Due to this volume change, it would actually cause an instantaneous pressure spike when compared to normal operating temperature, normal operating conditions. Water fording. We got through the rocks, we've been going through performance, but now there's a small stream ahead of us that we need to get through. And when we think about remote locations or off-road vehicle trails, there's often small streams that we have to cross. Because we've been pushing this vehicle to the max, our battery pack's a little warmer than usual. And when it's submerged in the cool water, there could be a thermal shock within the free air of the battery pack. This thermal shock would result in a vacuum condition, causing high vacuum within the entire enclosure itself. Up next is DC fast charging. DC fast charging is rapidly charging the battery pack in a matter of minutes instead of hours. Now, as we rapidly charge these batteries, the cell temperature could increase. And with the increase of the cell temperature, would increase the free air temperature and pressure around these battery cells. Compared to normal operation, we would see a spike in both temperature and pressure outside of that normal operating window. Hill climb. So we just had a fun time. We got our battery pack fully charged after staying at the hotel, and now we see a mountain that we just really want to race up. As we start driving up this hill, we're going to have two things occur within the battery pack. Heat generated from the battery cells as we're demanding this vehicle to go up a massive hill, and altitude change. Both of these will create a delta pressure between the inside of the battery pack and the outside, and we would actually see a rise in battery pack pressure over time. Compared to normal operation, this would be a higher pressure and temperature value than our normal conditions. So we had a great time on vacation. We got to take our vehicle on some pretty extreme cases, but now it's time to pack up and go home. Now, because we had some extra money, we actually decided to fly the vehicle home, but keep in mind that a lot of OEMs and manufacturers will ship subcomponents by air also. So we need to keep in mind air transportation of these components. And during takeoff and landing, there will be rapid altitude changes that can affect the pressure within the battery pack. And if we don't consider these forces, this could cause extreme pressurization and underpressurization events that need to be accounted for. One thing to note though, the temperature range on this edge case is a little bit smaller because it's just going to be ambient with whatever the aircraft is under. The last edge case that we're going to discuss today is emergency degassing. And during an emergency degassing event, temperature and pressure will likely rapidly increase within the battery pack. Compared to normal operation, these events will be significantly higher than the pressure and temperatures experienced within the pack, and adequate venting will be required. So now that we've covered these edge cases, let's talk a little bit about how to design around them. And we're going to be talking about design considerations for both the system and for the venting. So talking about performance, DC fast charging, hill climbs, and air transportation, there's a couple things we can do. One, on the system level, is to minimize the amount of free air that's within the battery pack. Tight packing efficiency, putting all your components very close together, and minimizing the amount of free air will reduce each one of these load cases. Secondly, if we can do anything to try and increase the cooling of the battery cells and reduce the overall temperature variation, this will also be beneficial to the values of max pressure and max temperature. Now, in regards to venting, if we take a look at a burst vent, we would want to be able to increase the amount of airflow going through this vent. And this can be achieved through either a high permeability membrane, so a media membrane that would allow for high air to go in and out, increasing the quantity of vents on the battery pack. So instead of having one, maybe two or three, or having a larger vent in total. So designing just a larger vent than the normal one that's offered. In regards to resealable vents, we would want one that has high airflow, similar to the 3 points above, but we could tune the resealable opening pressure. So instead of opening at 50 millibar, maybe it'll open at 20 millibar or 10 to enable high airflow at low pressures. Now, when we think about design considerations for rock impact on the system level, there's two main paths that we could possibly take. One is increasing the battery enclosure stiffness. Because the primary pressure change is due to deformation, anything we can do to increase the stiffness will be beneficial. This can be through thicker materials, changing cross-sectional geometry, or even maybe a material change from a steel to a composite, as just a few thoughts. Now, another avenue that we could take is the addition of a skid plate. This is often seen with off-road vehicles today and could be another option. For venting, with a burst vent, there isn't a lot we can do besides either changing the airflow or validating that max pressure during testing, such as having a rigorous validation process to make sure that we've encompassed this load case. For resealable, however, we can change the opening pressure to make sure that the pressure event does not exceed a certain value. If it does go above that value, though, there might be a slight vacuum loading when the battery pack enclosure returns to its original shape. So we would just have to keep this in mind for this edge case. For water fording, anything we can do to change the thermal conductivity of the material will be beneficial. So if we can change the rate at which the air changes temperature, we will then affect how high or low of a vacuum condition will happen. So changing from a steel or a metal to a composite or plastic will impact this rate. Now, another option without changing material could be to add some insulation to the battery pack. Now, on a venting side, really the best way around this would be either increasing airflow or the addition of venting above the water line. That way, when the vehicle does go through the water, your vent is above, allowing continuous breathing during that entire submersion process. Lastly, when we think about emergency degassing, there's kind of two different avenues we can go, and that is a burst valve or a burst vent or a resealable vent. Taking a look at burst vents, we can either have high degassing airflow. The burst vent itself will have high degassing airflow when compared to a resealable. But one nice benefit of this vent is that it's going to be continuously open post the event, which means if the initial emergency degassing event had a high pressure spike, but then decreases over time, this vent will enable high airflow during the entire event, versus a resealable might close up after that initial pressure spike occurs. However, the resealable will open up at a much lower pressure, which could enable some higher air or hot gas to escape faster. So kind of two different avenues of design when we think about designing around emergency degassing. Now, in conclusion, there's a lot of systems level design that can impact the venting requirements of a vehicle. And things that we have to keep in mind are what edge cases will the vehicle see? Where are the location of the vents? What's the material of the enclosure? And what's some of the surrounding structure, just to name a few. Now, we believe that it's important to have conversations with your venting partner early in the development process and while setting specifications, as there might be some benefits that you get working with a venting partner that enable some systems level optimization. For instance, if you have high airflow and relatively low pack pressure, you might be able to make your battery pack a little bit thinner, saving some weight on the vehicle. Now, we believe that Donaldson would be a great venting partner for your application, as we provide advanced venting solutions designed to enhance product quality and performance while increasing your productivity. And this is through integrated solutions, advanced technology, and exceptional global support. And with this is kind of the Donaldson value, which is we can design, develop, evaluate, and validate all in-house. And as we look to the right, here's just some of our lab scale testing of rock impact on that 20-liter enclosure. At this point, I'd like to thank you for your time and now open it up to any questions the audience may have.
Thank you for the presentation. Now we'll begin the Q&A session, so please submit your questions by clicking the Q&A button on your screen. I see we have a few questions submitted already. If you could begin by reading the question aloud, that would be great.
All right, Matt, the first question we have is, in case of a pressure burst, what is the typical pressure at which the valve bursts?
Thank you, Shane. For the Donaldson dual stage burst product, we state that the vent will open up by 350 millibar. So when designing around a case, 350 will be the max pressure the pack will see prior to the vent opening.
Thank you. How do you balance designing for edge cases versus normal operation?
Thank you for that question, Shane. That's actually a pretty good question. And I think a lot of it comes down to what is the application that the vehicle or end system will be used in. In order to have a robust vehicle that will survive the entire life of whatever application it will be into, we do need to consider those edge cases and make sure that we have designed around them. As the last thing we want is a customer in the field having a premature failure on their hands. Now, if we consider all edge cases and include that with our validation, we might see that the edge cases just have a lower occurrence. So if we take a look at, say, pressure cycling, we might see a lot higher pressure cycles at a lower pressure, but we might just see a few excursions, say 10, 100, or 1,000 instances where we see slightly higher pressures. While these occurrences may only happen a few times, including them with the validation and ensuring the product is good to go will help peace of mind for the customers in the end of the day. So I think in all, we need to include those edge cases while we go through the validation, but understand where the vehicle or application might go. An off-road vehicle will not have the same edge cases as, say, a minivan or a small commuter car.
Okay, thank you. Did you try these extreme scenarios in the racing competition Extreme E?
For the edge cases that we discussed today, most of these were done at the Donaldson facility in our validation labs or through our modeling team and our calculations here. So these were not tested in the Extreme E sport, but they were tested on either subscale packs or through our modeling.
Okay. Another question on that topic of modeling and simulation, would you be able to support pack or module level venting design by CFD simulation?
We currently do have some capability for CFD here at Donaldson, and we have done some partnerships with OEMs for development and working through their edge cases. So it's definitely an opportunity that we can partner with and work through with a potential customer or client.
Okay, thank you. Are those results dependent on the cell type?
That is a great question. From the information that we know at Donaldson, it does appear that cell type does affect the thermal runaway. However, we do advise that you communicate with the battery pack or the battery cell manufacturer to get the exact values. Just taking a look at some technical data sheets, it appears, based on energy capacity and also geometry, you can have different thermal events. So these are going to be good questions to ask the cell provider and then kind of communicate with your venting partner as a triangle to understand what are those events and how can we properly account for them from a venting aspect.
Does it make sense to have two vents just to produce flow through? Maybe it helps with condensing water drying.
That's a pretty good and interesting question. If we think about a normal breathing vent that's used on an electric vehicle with, say, that ePTFE media, we do allow for gas to go in multiple directions, all within one vent. So if, say, we use two of these vents on a battery pack and connect a small fan, we would allow for some sort of breathe through of the entire pack. But also during normal operation, having one or multiple vents will enable constant air exchange and effectively do the same effect that you're discussing here. So without a lot of, basically using an off-the-shelf vent from Donaldson, we would be able to achieve this.
When would you recommend a dual stage burst or a dual stage flex vent?
That is a really good question. And a lot of it is going to be designed around the application and also what kind of customer requirements we have. If we take a look at a dual stage burst vent, the benefit is once the thermal event occurs, the vent is fully open and enabling high airflow from inside the pack to outside the pack. And no matter what pressure drops to within the pack, we're still going to allow continuous high airflow. But a dual stage flex vent will enable opening at extremely low pressures. So for instance, when we take a look at our edge case of DC fast charging, the flex vent will enable for overall lower pack pressures because we'll be able to exhaust that higher pressure at a much lower value. So when we think about designing from a systems case, a flex vent might enable for some more optimization and weight saving, but the burst might be more beneficial during that thermal runaway mitigation strategy. So it's going to kind of be a question that we have to work through in terms of what are the priorities of the customer and what are the, where will this vehicle be going to in terms of end application.
Okay. How many vents does a typical battery pack have? Only one or multiple?
That's a really good question. And it really does depend on the size of the vehicle. As we've seen electric vehicles evolve, we've seen, and also hybrids, we see a wide variety in size of battery packs, ranging from plug-in hybrid vehicles that have a small battery pack or even multiple small packs, up to large skateboard platforms that have a battery pack the size of an air mattress. Now, if you're using an off-the-shelf valve, say the Donaldson dual stage burst or dual stage flex, if you're designing around a small battery pack for a plug-in hybrid, you'll maybe only need one of these valves for that smaller pack. But once you get up to the larger skateboard platform, you will likely need multiple vents just to ensure you have adequate airflow in and out of your pack to prevent high pressure loading of the entire pack itself. So it really is dependent on the application, but we have some calculators internally which can now allow us to easily figure out what the optimum number of vents is for your application.
If the pack-free air volume is occupied by an insulating material, not by air, would the internal pressure changes be minimized?
Yes, if the free air volume is reduced, there will be a reduction in the overall pressure spikes seen by the pack. So that would be a good strategy to help mitigate and might be a great approach. The only question would be, would that extra thermal insulation affect any sort of cooling strategy for the cells themselves?
Okay. Another question related to that. As you mentioned, one of the solutions should be to reduce the volume of air inside the pack, but the pictures of the venting devices seem to have large sections inserting into the pack, which might occupy a large volume of the pack. Does Donaldson have a venting device with a short insertion length?
That is a great question. And inside the portfolio of Donaldson for off-the-shelf solutions, we do offer several both quarter turn snap-in vents, which occupy a very low volume inside the pack, and also threaded vents, which if the battery pack is a casting or some sort of geometry like that, we can actually thread into the geometry or thread into the casting itself. So we do offer some off-the-shelf solutions that do fit that. And we also do some custom designs, which could either bolt on to the outside of the pack or install via a snap feature to mitigate the amount of leg or a portion of the vent that is inside the battery pack.
Okay. I have a question here. It says, is there any delay introduced before the valve is opening?
If we take a look at our dual stage flex valve or most resealable valves, there will not be a delay as the valve is just responding to the pressure. And additionally, with the dual stage burst, it is responding to pressure. However, you might see some hysteresis upon closing the valve as the valve goes down to touch back onto the seat. But this hysteresis is pretty nominal, so the closing pressure will be similar to the opening pressure.
Thank you. We have time for one more question. I think we'll end it with, what was the most surprising part of the venting solutions design process for you personally?
When I kind of came to venting, I never really considered what edge cases might actually be some of the big drivers. And I grew up in a rural farm where I often drove on dirt roads, and we had a lot of like gravel hitting the undercarriage of our trucks. And I never really thought that or like sliding on top of a small rock while off-roading would cause such a large instantaneous pressure rise. And it really made you think, as we develop electric vehicles, there are just new edge cases that we normally didn't consider on a previous vehicle. So it was just a little bit of out the box thinking, and it kind of made us say like, okay, we really need to sit down and understand where these vehicles are going to go, which is, I think, pretty exciting because you have so many different vehicles with so many different applications to consider. It really kind of put a smile on my face thinking about where these products might go all over the world. So with that, unfortunately, we're out of time, but I'd like to, I appreciate everyone for phoning in today. And if you have any other follow-up questions or would like to learn more information, please feel free to reach out either to myself, matt.good@donaldson.com, or feel free to go to our website and reach out to our general email there. And we would love to hear from you. Thank you very much and have a great day.